So let's get started. So hello and many thanks for attending this session on how artificial superintelligence will solve human disease. And that's part of the King's Festival of Artificial Intelligence 2025. So the festival has been organized by the King's Institute of Artificial Intelligence. And this is the third year that it has brought a wide range of free events to both King's and external audiences to showcase the range of AI expertise across King's breadth. So this year, there are over 45 separate events happening over 5 days between May 20th and May 24th. So if you'd like to find out more about the King's Institute for AI, join our mailing list, or find out about other events in the festival, please do go to www.kcl.ac.uk/AI or follow the King's Institute on social media. So a bit of housekeeping. Please ensure that your microphone is switched to silent. And please add your questions to the Q&A throughout the talk, because we'll pose these questions to the speaker after today's presentation. All right, so to get started, today it's my pleasure to introduce Dr. Hector Zenil, who is a senior lecturer or associate professor in biomedical engineering at the Faculty of Life Sciences and Medicine at King's College London. He conducts research in biomedical systems engineering, leveraging and combining tools from complexity science, computability theory, and causal AI. He is the sole founder and chief visionary officer of Oxford Immune Algorithmic. That's an AI spin-out from the University of Oxford. And he was the CEO for its first 5 years. Dr. Zenil, please take it away.
Thank you very much, Gustavo. I'm very happy to be here. And thanks to the King's Institute for Artificial Intelligence to organizing this great event. It is great for me to be opening the festival. And I will be speaking to you about how artificial superintelligence may or will end disease. And by this, I mean preventable disease, but even the word preventable has changed over time and is going to keep changing even faster with AI. So if I had to summarize my own research, I would say that I teach computers and AI to understand and deal with randomness. And I also try to teach them about generating models of the world that are more like computer programs or mathematical functions or equations than more traditional statistical approaches based on pattern matching. So I'm trying to go further away than the current AI as it is today. And this is because we believe the human mind is not statistical or only statistical. And we have published multiple papers in this regard. One of them actually got a lot of traction with the world media. Here on the screen, you can see one from one article from the New Scientist. And it is what we called back then a kind of an inverse Turing test. So if you remember, the Turing test is about asking questions to a computer. And if you are fooled many times enough, you cannot distinguish it from humans. Basically, you can say that the system is intelligent. In this case, actually, we did the opposite. So we asked people some questions as if they were computers. And we asked them, okay, could you generate the best possible randomness? Or how do this configuration of objects look random or not to you? And it turns out that we couldn't explain all the choices by humans with regular statistics. We had to go well beyond statistics to a theory that is called algorithmic information theory to be able to explain those choices. And let me give you a very simple example. Back then, when you had to remember phone numbers, it is true that you would remember better a number that has a statistical pattern. Something like if it is 5757 5 times, it will be very easy to remember, right? But sometimes we can remember things that are not completely statistical or don't have patterns, at least not trivial statistical patterns. let's say that the phone number is a sequence of natural numbers like 1, 2, 3, 4, 5, 6, 7. Actually, that is a number that is called a Borel normal number, which means that basically there's no statistical patterns in it. So any subsequence is represented the same number of times. But yet we can remember it because we have a model in our mind that tells us that the next number is basically just adding one number at a time. And that's what statistics is missing, because if you were looking for a pattern in that sequence, in that phone number, you wouldn't find it unless you had access to a function. In this case, it's the successor function. And our mind works pretty much like that. So the question is, why do we need AI in healthcare and medicine? And what type of AI that would need to be? And we need it because we need to scale up. Currently, there's a huge staff shortage. Hospitals and health professionals are overworked, showing signs of great fatigue. And we also have a growing elder population. So to deal with the demand, we have to scale up technology. We also have to address unfair disparities, things like access inequality. People in remote areas have access to suboptimal care because they cannot go easily to a good hospital or a good lab. And actually, it is very sad, but 1 billion people never see a doctor in their lifetimes. Care has also become very impersonal. Access to preventive healthcare is difficult, expensive, or even inexistent. And most of it is population-based, one-size-fits-all healthcare that is not preventative. We also have very slow and imprecise processes, too many bottlenecks, including, for example, blood testing. If you want to get a blood test done with NHS, sometimes can take even weeks. And diagnosis is mostly based on symptom pattern matching and not the root causes. So that's some of the reasons we require AI in healthcare and medicine, because it is also breaking under its own weight. More than 200 million medication errors occur in England, costing a lot of money. But more important, misdiagnosis, for example, are the cause of many deaths around the world, only 800,000 in the US. So what is artificial intelligence to begin with? So one important thing to understand is that all definitions of AI are anthropomorphic, and that means that they are human-centric. Therefore, they are not very objective. Usually, AI is related to any automated task traditionally conducted by humans that a machine can perform with some agency or illusion of agency. And here is a very old example of a beautiful automaton that is able to write and draw, that is exhibited in a famous museum. So the next question is, what is artificial general intelligence? And there's a lot of hype around talking about AGI. And the typical definition is that AGI is an AI that it is as good as any human or all humans at all human tasks. This is another very broad, ill-defined human-centric definition, because we have even trouble defining human intelligence. But what is then artificial superintelligence or ASI? And one common definition that is used by many researchers comes from a book called Superintelligence, written by Nick Bostrom. And his definition says superintelligence is an intellect that is much smarter than the best human brains in practically every field, including scientific creativity, general wisdom, and social skills. This definition, in my point of view, is very problematic from all angles. We have to define what is an intellect, what is wisdom, and even social skills. It turns out that this definition is actually even more problematic, perhaps, than only AI. And one question that we have asked is whether we can define superintelligence in a less human-centric fashion, because at the end, it is not even a property of humans. By definitions, by definition, we are not super intelligent because we are trying to define something different beyond human intelligence. So in some way, we have tasted and tested what I call narrow superintelligence. And that already exists with things like calculators. Calculators are better than any human being, and perhaps even all human beings combined at things like arithmetic. They can do operations, arithmetical operations, almost in no time, and almost no matter how long. And that is also the case with computers at many other tasks, including what we thought before that was only possible by humans, like face recognition, now also theorem proving for the last decades, and even playing chess and Go, weather prediction, solving equations. All these things are much better conducted and performed by a computer than a human being. So in some way, we have tasted narrow superintelligence. And AGI, AI, and even biological human or animal intelligence can be thought as special cases of superintelligence in some way. And calculators and computers are also an example of symbolic AI because they manipulate symbols, either numbers, words, and so on. This is going to be useful for some of the next slides. So two of the properties that recently have come up as fundamental for intelligence is model abstraction and planning or prediction. And this comes from several researchers, including Jan LeCun, in a recent paper that is available online, and you can see the link on the screen. And model abstraction and planning are two of these features that these leaders believe that are fundamental for intelligence and therefore for AI. And modeling abstraction is a type of inductive inference. These are big words, but basically they mean that you can say something about what you want to understand or explain. So it is related to understanding or representation of that object or that event. And planning or prediction is a type of deductive inference, which basically means that you can say something about what follows from a sequence of events or observations. In other ways, it is some sort of simulation of realistic future scenarios. And a point that we have been making, and you can see the recent paper that we posted recently, is that model abstraction is very close to data compression. Because a model of the world is a representation that aims to capture the main features of interest of something. Let's say it is a cat. What you want to capture is perhaps their size or the particular way of walking, the whiskers, and so on. So the process starts from observing something and ends with an explanation, a description, or a representation. And this is what is called the problem of inversion. The problem of inversion is looking at something and then coming up with its explanation or the model that explains it. And the model must discriminate between noise, and noise is as a form of randomness. So that's why I'm trying to teach AI about randomness. Because noise is not important to explain the data by definition. And it is the features that explain the data. As I said, for example, in a cat, it is very important perhaps that they have like elongated eyes versus just having legs, because having legs doesn't characterize cats only, it characterizes more animals. So you have to be careful of what features you actually capture. So a model that includes every detail is not really a model, because it is just the data itself. So in some way, a model has to be something compressed. And planning using the framework of algorithmic information theory turns out to be the other side of model abstraction. Because once the main features are identified that capture the essence of a sequence of events or an object like a cat, for a model to be useful, it should be able to run in reverse. In other words, you move it forward to produce the original data. So the explanation should be able to reproduce the data. This is also called abductive inference, which is another big word. But in other words, it's just basically making the best prediction with the available information at any given time. So why current generative AI is poor at conducting all this, and that includes large language models or LLMs. It is true that LLMs are some sort of compressed version of the World Wide Web. And the problem is the model is not very efficient because it comes with a lot of noise. And it is not mechanistic, so you cannot run it in reverse with high accuracy. You can try to run it in reverse, but it is highly statistical. And you can see on the screen what we all already know, that it is pretty bad at reconstructing hands, for example, fingers. And there's a very good explanation about it. And by the way, this is not an old image. I generated this 2 days ago with ChatGPT 4.0. So these are still issues that the best frontier models still have. And the most reasonable explanation is that because these are statistical approaches to data, what you have is that an LLM always considers what is the likelihood of having a finger next to another one. And it is more likely than not, because we only have 2 fingers on the extremes that don't have neighbors on one side. But if you're asking the probability of any finger to have a finger neighbor, basically is more likely. And that's why it keeps basically printing more fingers around until there are too many and says, okay, I have to stop now. But in other words, it often doesn't get it right. And you can see on the screen, for example, a person that even has 2 right hands or right arms.
Excuse me, Hector. There are people saying they
so
can't
it
see
lacks this symbolic understanding to reproduce data. And it performs very poor at planning or prediction. Just for example, predicting that any human being should have 5 fingers. So LLMs don't look like they are the solution for AGI or superintelligence. Here's another example that you may have seen online as well. This again, I did it myself 2 days ago only, with again one of the best models of ChatGPT. And you can see how interesting it looks, because Lisbon, for example, was, according to ChatGPT, in Spain. And all sorts of oddities on this map. So LLMs look very intelligent because somehow they hacked our user interface, which makes them appear more intelligent than they actually may be. So LLMs are somehow in what I call the intelligence uncanny valley, which applies usually to robots. Robots that look very human-like are kind of scary because they look very much like us, but we know they are not. So that happens with LLMs because they look very much like us in the way they speak, but actually they are kind of fooling us most of the time because they are statistical tools. So this is another problem with LLMs. If you ask them, for example, to do an arithmetic operation, and they are getting better and better over time just by ingesting more and more data, and with some other programs that they put on top of LLMs, and we are going to see what does that mean. But if you pick 2 random numbers and you ask an LLM to add them up, if they don't have some sort of engine that captures those cases and just runs the statistical approach from the core LLM, it's going to most likely get it wrong. And it is kind of embarrassing because computers and calculators, as we saw, they excel at doing arithmetic. So how it comes that actually if you ask a computer, it gets wrong. But this basically shows what are the problems. If an LLM hasn't seen that data in the training set, it's not going to be able easily to come up with the right answer. And there are all sorts of issues with LLMs. This one is, for example, called one-pixel attacks, where you have, and this is not an LLM, this is generative AI. So this is a convolutional neural network trying to classify or tell what is on the picture. And you can see examples, for example, of a bird. But if you only change 1 pixel on the image, the classifier tells you that it is a frog with very high confidence. So that's why this is called a one-pixel attacks. You just change something slightly, and the neural network basically gets it wrong. It breaks. So it is very fragile, and that's because it doesn't have a model of what is a bird. Basically, just by changing a single pixel, it breaks everything. And this is still the case. These are all examples where you can still do pretty much this with convolutional neural networks. This is another example where randomness is key. So what you see on the screen are 3 images. On the left, it is a school bus. Then you can add some noise to the image. And to us, it still looks like a school bus. But a neural network is going to be completely confused. So we call this the panda test, for example, because once you add noise, the neural network actually thinks that it is something completely different, like it is a gibbon. So imagine this kind of attacks in the context of healthcare and medicine, where it could be used for malicious purposes, like if you tamper with data, like a CT scan or an MRI, we just changing something slightly, you would break the system. And this is the kind of things that you don't want. Even if it is not malicious, it could be just an error. And basically this tells that with very little, the system can break. And you want rather something very robust. This is another type, basically just by changing the position of the objects, the neural network gets it wrong again. And this is a type of attack that we proposed, and it is very interesting with LLMs. So we call it change of opinion attacks. And you may have experienced this because LLMs are basically kind of trying to please you by finding the most average answer to something. And what we found is that actually proprietary and proprietary and non-proprietary LLMs have different thresholds of change of opinion attacks. So for example, proprietary LLMs are easier to be attacked in this way by humans, whereas non-proprietary open LLMs are easier to attack with other AI agents. And we used all this research to basically try to explain the problem of AI alignment. AI alignment is basically how we align AIs to hold our values and human interests. And the problem is that we have proven mathematically that it is impossible to control them and be certain that an agent is going to remain aligned with human interests. Let's say a task that is being given. But actually what you can do is to have other agents to help you to keep it in line. And you can have some sort of alliances with agents and humans to try to control all other agents. So should we trust current AIs in healthcare and medicine? Well, as we have seen, that is very difficult. And you have here another example from a couple of years ago where Google's Gemini was recommending to glue pizza and eat rocks. So sometimes it can get very troubling if it is not under supervision. And one of the main problems is what I was talking about before. So machine learning at their core, what they instantiate is some sort of a machine that is related to correlation and not causation. They don't produce models of the world. And this is also related to how they evaluate how far away they are from the world itself, their representation against the world. And that is called usually a loss function. So a loss function is basically a metric that neural networks implement to see how far they are from the ground truth. But these metrics are based on correlation, not causation. So let me give you an example with a convolutional neural network. This is obviously an oversimplification of how they work. But let's say that you want to classify cats and dogs, recognize what is an image of a cat and dog. And after you train with many labeled images where you actually went through labeling each of these images, then you give the neural network unlabeled images and you expect it to basically tell you whether it is a cat or a dog. So if it were a cat, you would expect the neural network to actually pick up some of the main features of a cat, like having long whiskers or narrow pupils and so on. But these are usually neurons in a neural network that you cannot have a direct access to. So that's why it is called a hidden layer. And this is also why it is called a black box, because usually you only see what you input to the neural network, and this is called the input layer, and then the output, whether it is a cat or a dog, or anything in between is hidden from you, and that's why it is called a black box. Only opening the black box, you know what is inside, and we are going to do just that in this illustration. So this is what you would have expected for a cat. This is like the activation pathway of these neurons to get from the input, which is a cat, to the expected output, which is a cat. And then you show it a dog, and what you would expect is, again, to pick up some features from the training set. After seeing so many pictures of cats and dogs, you would have expected that neural network would say, okay, they have a larger nose, perhaps. They have round pupils instead of elongated, and so on. But it turns out that when you open the black box, in quotation marks, turns out that they are picking the completely wrong features, or the unexpected features, because they are not necessarily wrong. And there was a study where they showed that actually some of these features that the convolutional neural network picked up were related to whether the dog was outdoors or not, or the cat was indoors or not. And this is not a kind of a fundamental feature, it's kind of a bias from the training set. But that can always happen. And again, this is because the neural network is not abstracting a model of what is a cat or a dog. It is just picking up features from the training set, which could be highly biased. So how do we fix these problems in deep learning? And one idea from Judea Pearl, who is a highly regarded researcher in causality theory, is to build machines that understand cause and effect. And that's basically what I've been trying to do in the last few years. So things that an artificial superintelligence can do that artificial intelligence or even artificial general intelligence cannot do is go beyond this kind of a correlation approach to data. And artificial superintelligence actually was kind of solved theoretically in the 50s by a researcher called Ray Solomonoff. And the theory is called algorithmic probability. And it basically answers what is the best, optimal, and smallest model that can explain a piece of data. And on the other hand, what makes optimal prediction possible from the information available. So everything that superintelligence basically requires is included in this algorithmic probability theory. And it's kind of the ultimate Bayesian abductive method. I think these are big words, and many of you may not be familiar with, but maybe some of you are. But this is basically saying that this is a mathematical theory of very important form of inductive and abductive inference. So who was Ray Solomonoff? He was a researcher in AI. He participated in this very famous Dartmouth conference, where basically all the founding fathers of AI were present, including Marvin Minsky and McCarthy and even Shannon. And it is the place where they come up with the term, and it was coined for the first time, artificial intelligence. And there was an agreement that basically algorithmic probability was solving AI, AGI, and superintelligence, and they some researchers even call it the miraculous universal distribution. That's because of the way it produces the data. But it was highly theoretical and difficult to implement. So the question is, can superintelligence be actually solved in practice? And we believe so, and that's what we have been working on for the last years. And it's very, very similar to what happened with artificial neural networks. They were kind of solved theoretically between the 50s and 80s, from the definition of multi-layer perceptron to the concept of neural networks that are Turing universal. That means that they can implement any computable function. They are general purpose computers. But it was not until the early 2000s or 2010s that the practical side was solved. In other words, they were useful for something, for practical application. And there's no agreement of a single breakthrough that made that possible, other than we have access to more data from the internet and we have more computer power. So we believe this is the same case with superintelligence and the theoretical side of it. So in practice, what it's going to take is actually a lot of computer power, which we are getting access to, and that's why we are starting to test it. And the surprising thing is that we don't require as much data. So actually, the other approach is much more data intensive. So this is a little bit of how algorithmic probability can be explained. So it connects two fundamental areas of science, classical probability and computation, in a very beautiful way. It is also the accepted definition of randomness, because it defines randomness as something that is uncompressible, unpredictable, and uncharacterizable. That means that, for example, you cannot come up with some sort of model that is shorter than the data. So you couldn't characterize the object or the data with a model that is shorter than the data itself. And it is also very universal. This is not like a toy metric. Many researchers try to come up with different ideas for the same concept, and they turned out to be equivalent to each other. So it is a very strong mathematical theory. And basically, it quantifies the probability that a random model actually characterizes the data. And what we do is to have some sort of engine that when given a piece of data, we break it into small parts, and then we try to find a small model for that part, and then we put it together. And we keep doing it all the time. So basically, we can explain larger pieces of data from smaller ones. And then we sort the models from which one is the more likely by size to the less likely. And it's not only the size, but also how much we can predict with that small model of the original data. And every time that we have access to more data, we can keep updating the model. So that's why it is optimal in what is called the Bayesian form. And this is some sort of neurosymbolic computation, because we have kind of this both parts. We can deal with uncertainty, just as neural networks can do, but also with symbolic computation, because we can manipulate objects and come up with very precise models that are computer programs that, when run in reverse, basically produce the original data. So Marvin Minsky, who is one of the fathers of AI and was in this original conference, actually has said that algorithmic probability may even solve science. There's a very nice video from the World Science Festival in New York City in 2014, a couple of years before he passed away, where he basically acknowledged that he would have liked to devote his life to algorithmic probability because it was so powerful and because it could even solve science. And you can also find some references from some people, not that I'm endorsing any of them, but Elon Musk and Ilya Sutskever have said that compression and algorithmic complexity, which is basically another name for algorithmic probability, are fundamental areas and concepts for the future of AI. So what we need to solve current AI, and it is already happening? Well, what we need is to find ways in which we can explain the data mechanistically. And here are two examples. One is with basalt columns that you may have seen in some places, including the north of Ireland, and fairy rings that are also quite not very rare in the UK. So these are mushrooms that grow in a circular pattern. One is a completely physical phenomenon. So these are hexagonal shapes as a result of very hot lava in contact with water very quickly. These are the kind of shapes that they form. And this one is a process of living organisms that basically start from the center, but they exhaust their resources and basically start growing towards the periphery. So there are a lot of patterns here, but if you want to use some sort of statistical neural network, you wouldn't be able to get most likely to the cause of what produced these patterns in the first place. And that's what we are looking for frameworks that allow you to have access to that generating mechanism. And this is what science is all about. So we had models of the solar system. In this case was a wrong one because it is a geocentric model, yet it was able to predict a lot about the movement of the planets, but it was not a simple model. It was quite complicated, especially with compared with the heliocentric model. So that was the whole difference between one model and the other one. So with the heliocentric model, it was not only simpler, but you could explain even more because you could extrapolate it, for example, to galaxies and so on, because it is based more on how gravity works rather than forcing Earth to be in the center of the universe. So science pretty much works in the algorithmic probability way, trying to find shorter but more powerful models over time. And here is another example with what is the Antikythera device, an ancient device from Greece, where you would have some sort of initial conditions, and then you would have a prediction about, for example, the movement of the planet or eclipses and so on. And this is basically the explanation for all that. So the sun, it is related to the sun cycle, and you have to come up with gears that are the right size to come up with the right prediction. And this is what is lacking in current statistical approaches of AI, and what we are basically adding to these models. This is another very interesting example that I like a lot about the distribution of cars on the road. So you may have seen that the time between cars, if you are an observer on the road, distribute as in this way. So between them, there's always like a short period of time. They come in batches, in other words. Obviously, they cannot be separated by zero because they will be occupying the same space. In this case, I guess it is like just a fraction of a second, so the car was very close to each other. But in general, they are very close to each other, and then you have only a few batches of cars that are separated from each other. So this is the statistical explanation, but it's not telling you the cost. And for me, and keep trying to find the cost was very interesting. So the cost, the origin of this distribution basically was left for scientists and researchers to come up with. It didn't come from the model itself, because this is a statistical model. It's just telling you the times between the cars and so on. And the reason is that actually there are always slower cars in the way. So the faster cars accumulate behind. And that's why we see batches of cars coming all the time. So actually you can also test this, because if you add additional lanes, then you start destroying the pattern, because then cars can take over others and the distribution looks completely different. So this is a very nice explanation of how something that has a cost basically changes the statistics, but the statistics themselves don't tell you the cost. So this is what we are trying to do. So to combine the best of both worlds, we have some sort of universal algorithmic machine learning approach where we combine algorithmic probability with neural networks. And what we have at the end is some sort of model of the data, which could be just a mathematical function, an equation, or a computer program that explains the data. So this is a sequence of natural numbers in binary, for example. And then we can find small models that can explain part of the data when it is broken down into small pieces. And then when putting it together, actually you notice that it is a model that you already know, and you can produce the function that explains the original data. That's basically how it works. We published a paper on Nature Machine Intelligence, and Nature themselves produced a very nice video on their own initiative. We didn't pay them anything. It was just to promote our paper. And if you scan this QR code, you're going to have access to this video that explains very nicely what we call causal deconvolution. And this is exactly what we mean by teaching computers to learn randomness, because they have to disregard randomness in order to come up with a model for the data that it is then predictive. So how can we measure superintelligence? And in a very recent paper, we also came up with this metric. We call it the super arc. For those familiar with the arc test, that was the inspiration. But the arc test claims to measure artificial general intelligence. And what we wanted to measure is superintelligence in the context of algorithmic probability. So we tested all these LLMs for the prediction power on integer and binary sequences against artificial superintelligence implemented by our methods. And as you are going to see in one of the next slides, actually, we did much better than even those LLMs that are specialized in time series prediction. So superintelligence is going to be key for things like precision healthcare and predictive medicine. In my own group with a startup, we are also building medical devices that collect data over time. And what we are trying to do is basically reverse healthcare and find key patterns, what we call disease signatures for early detection and predictive medicine. But for all this, we need to deal with deep longitudinal datasets, impossible for any individual human or all combined to analyze. So that's why we need very powerful AI. And we need the kind of framework that I'm talking about for prediction, because usually in healthcare, what we have is this kind of data, so longitudinal data, or ideally what we should have, because the current system basically takes snapshots. And in the best case, medical doctors only look at the last previous result and against the new one. But now we have clinical and biological evidence. There is a very beautiful paper published by a Harvard group in Nature at the beginning of this year, where basically they show that even for blood testing, every people is different. They have a personal set point or baseline over time. And we should be learning those ones in order to flag for small changes, because even if you are within the normal blood testing values, you may not be healthy. So here are some examples of what we call disease signatures. So for example, bacterial infection has a very specific signature compared to a viral infection, because in one case, neutrophils, and in the other one, lymphocytes go up or down in counts. And that's the way in which you can differentiate one or the other. But if you only had like a single snapshot, it's much more difficult. And you cannot do early prediction, early detection and optimal prediction. So this theory is basically proving very useful for these kind of cases and to come up with causal models, as we're going to see in the next slide. So this is the result I was telling you about, where we basically outperform LLMs at predicting sequences using the method based on algorithmic probability. And these are even LLMs that are specialized exclusively in making predictions for time series. So in other words, they are very far away from, if not AGI, because that is very difficult to test. As you may remember with the ARC test, some are claiming that they are already there, but then they change the test and now they are not performing very well. In this case, we proved that this test is very stable. It is very difficult to fool, and all LLMs are basically almost at the bottom. They are they deal very poorly with model abstraction or generation and with accurate prediction. But once we have these disease signatures, what we can do is to move to what we call disease networks. So two biomarkers that are related to each other, usually they are said to be correlated, and you can create some sort of a correlation network. But then you actually can create a causal network that is some sort of set of hypotheses of how each thing is related to each other causally. So when two things are correlated, basically you create another point where it is your hypothesis that those two things may come from the same cause. And then those hypotheses, you try to confirm them or reject them. And all this basically to create some sort of digital twin of people. So to understand the body as a model with which you can do things like interventions and then simulate the future trajectory of that individual. So what we came up with is the causality ladder from Julia Pearl, the researcher that I talked about a few slides ago, and apply everything that we have developed in the last few decades, causality, to this kind of framework. And we added an extra layer, which we call algorithmic information dynamics, which is based on all these ideas around algorithmic probability, but it combines them with all these other ideas of intervention and what is called counterfactuals. So counterfactuals are things that you can imagine that could have happened if things would have been differently. So let's say if I hadn't started smoking when I was a teenager, how things would have changed. I'm not a smoker, by the way. An intervention is what happens, for example, if instead of taking this drug, I would have taken this other one. So you can do all sorts of simulation experiments with simulated digital twin of an individual to see how it may change in the future. And all this is basically to come up with some sort of very sophisticated, not only device, but an approach to healthcare that is very similar to, for those familiar with Star Trek, what was called the tricorder. So some sort of approach where you could detect disease and hopefully treat it before it becomes more difficult to treat. And that way, I think superintelligence is key for healthcare and medicine. And basically, in my group, we are trying to make superintelligence in healthcare and medicine possible. So I'm going to stop there to thank you and to take any questions.
All right, thank you very much, Dr. Zeno. I'm looking at the questions here and the Q&A page. So maybe I'll start off. So we have about 5 to 10 minutes for questions while we wait for the questions to be populated. I'm going to start with one. So looking at the title of the talk, right, which was brilliant, I'm wondering, how do you see the tests that you're proposing, or at least that artificial superintelligence will be able to bring? How do you see that interplaying with doctors, right? What's the role of doctors and clinicians with this new technology?
Yeah, great question. So what we are doing at the moment is to support doctors because, as I said, actually the health system is under a lot of pressure, as we know. So we are giving the gift of having more time by helping them with tools from AI. So at the moment, the idea is that they are always in the loop. They are supervising the AI, but maybe in the future, if we gain enough confidence and the AI is proved to be reliable enough, then we can keep or start leaving more and more responsibility to the AI side with less supervision, because that's another problem. We are not training enough healthcare professionals. There's a lack of doctors and nurses. So it is not that it's going to get any better. If anything, it's going to get even worse, because we also have a growing elder population in most of the world, including the UK. So there's going to be more demand, but we have even less doctors, nurses, and healthcare professionals. So we have to keep relying and hoping that we are going to rely more and more on technology, automation, and AI.
Great, thank you. So there's a question here. So it seems that there is a bit of a bottleneck around going from correlation networks to causal graphs. So manually checking the literature and etc. So is there a way to cut out human or our own biases?
Yeah, that's a really great question. There is indeed a real bottleneck into moving from correlation to causation. But the problem is that right now we are not doing almost any causation. So just moving a little bit the needle is helpful. And the idea is that eventually we are going to be able to automate some of this process, if not in generating the causes themselves, which is kind of what we are doing, but it is very mathematical, and sometimes it may be hard to interpret some of the output from the machine. At least I think AI is going to help us to find if someone else has already some explanation, and it's going to help us design experiments to confirm or reject those hypotheses. But that's a good question. So doing causality is very hard, but it should be what we should be doing. That's the main message.
Thank you. And then also about bottlenecks, but now a different type of bottleneck here. So you mentioned that there are too many bottlenecks within the NHS. So if the test diagnostics were sped up, for example, does it not move the bottleneck further down the care pathway before super early detection is fully in place? Or do you envisage ASI also speeding up treatments, including surgical interventions?
Yeah, eventually that's the main objective, but it may take many years, perhaps even a decade or more. So there are many bottlenecks, you're right, including regulatory ones. So how much we leave to the AI, for example, is going to be not only difficult from a regulatory point of view, but also social point of view. So how much we are ready to give AI responsibility, because someone has to be liable. And there's no way to remove basically the human aspect, because someone has to take the decision, and we cannot just blame the AI or whoever wrote the AI. But that's a great point. So there are too many bottlenecks, and basically we're trying to crack one at a time. We cannot change the whole system in one go.
Great. And now probably the last question. So how do you see this, everything that you show here, interacting with drug and therapeutic development pipelines? And do you think digital twins can be employed or replace clinical trials?
I think so. Eventually it will. And even now, current AI, because by the way, I think AI, even LLMs are fantastic tools if we understand them for what they are for. And we wrote a paper that has been accepted and is going to be published hopefully this month in Interface by the Royal Society on using LLMs to explore regions of drug combinations that humans may not have already explored. And these are combinations of FDA-approved drugs that when combined, they may be synergetic for things like breast cancer. And at the same time that they are synergetic, meaning that putting them together fulfill their purpose of attacking breast cancer cells, they are also not toxic because we don't want to kill the healthy cells. And in our knowledge, it is the first time that a drug combination discovery paper comes out, because what we did was actually not just to get the LLM output, but we went to the wet lab to validate what the LLM was telling us and see if it made sense or not. And then we fed back the LLM with the result of the actual experiment. And we got new hypotheses. So the whole point of the paper is to show that AI can basically help close the loop of scientific discovery, in this case of drug discovery. So I think it's going, even the current state of AI is already proving very useful, because even if it is not very creative, it still can deal with ingesting a lot of data and exploring perhaps regions that not every human is going to have access to or is able to ingest by themselves. But eventually, that's absolutely true. And I think pharma companies are already doing, if not, thinking, if not already doing digital twin technology for the purposes of testing drugs in silico, is basically called. So you do simulations first. I don't think it will ever completely replace, because at the end you have to prove that it is safe to give it to human beings and not only simulations, but we can hopefully shortcut the very long processes of drug approvals.
Perfect. All right, so thank you very much. Thank you to Dr. Zanil for sharing his thoughts and his expertise. And this event was truly wonderful and very valuable contribution to the festival. So thank you very much. Thank you to the audience. And please take a moment to scan the QR code that you're going to see shortly in your screen and answer one question to help us with our evaluation of the festival. So thanks for coming to this talk today. And just a reminder here that the festival runs until Saturday, the 24th of May. And there are lots of other events in the program, so you can find out more and register by following the QR codes you see. And if you attend an in-person session, you can also speak to someone in a festival t-shirt if you'd like to know more. So Thank you again.